This is a recording of my Darts 24 presentation. The title is Investigating the Correlations in Between TSD Measurements. The objective of the study is to develop a quality control tool for TSD measurements. The idea is to assess data quality and also detect anomalies in measurements. The methodology is to use mechanistic modeling or simulation, so the study is purely synthetic. It contains 1 million layered elastic cases covering a wide range of thicknesses and moduli, and each case produces a TSD result set as if a TSD machine was applied on the layered system and measured deflection slopes. And then a statistical analysis is performed, correlation analysis specifically between measured slopes from different lasers and also cross-plotting the results from different lasers. This is an outline of the simulated cases. You have here 5 layers. The Poisson's ratios are the same for all million cases simulated. The top layer, normally representing asphalt concrete, has a Poisson's ratio of 0.3. The second layer below, maybe representing an aggregate base, could be also modified or stabilized, has a Poisson's ratio of 0.35. And then this is the third layer from the top, representing maybe a subbase, has a Poisson's ratio of 0.35 as well. And then the fourth layer from the top, maybe representing a capping layer or a frost protection layer, it has a Poisson's ratio of 0.4, and then the last layer in the model, which is semi-infinite in thickness, has a Poisson's ratio of 0.4, maybe representing a local soil medium. The moduli ranges here for the top layer, anything between 1000 and 25,000 megapascals, second layer 100 to 8000 megapascals, third layer 80 to 600 megapascals, fourth layer 20 to 500 megapascals, and fifth layer, last layer, 15 to 150 megapascals. The thicknesses were also varied. The top layer, the thickness was varied between 40 and 450 millimeters. Second one, 150 to 300. Third one, 150 to 600. And the last one from 0, which is no capping layer or frost protection layer, all the way up to half a meter. Here's one example. Here you can see the modulus for this example for each of the layers, the Poisson's ratios, and the thicknesses. And here you have a footprint of the BAST TSD device called the MESAS. So we have 10 wheels, and here's the measurement beam. And this is the deflection slopes along a line just below the beam in the beam's direction, the travel direction. So this deflection slope curve was produced by considering all the wheel loads, and then as the machine is also delivering the reference laser slope as if it was a zero slope, this is done the same here. And for every case, there is a set of slopes that is being calculated. The slope at minus 450, that will be a slope collected or reported by a sensor that is 450 millimeters behind the rear axle, and then there's a slope at minus 300, minus 200, and then slopes in front of the rear axle, 110 millimeters, 210, and so forth. So there's an array of 10 slopes that is being reported, and in this case being simulated. Now, correlation analysis was performed between the readings of different lasers, and the correlation analysis was based on the values of the fraction of variance unexplained, that's FVU. And here you have a list of all the combinations. So here for a sensor at minus 450, it is perfectly correlated to itself, but then there's some changes in the variance, the fraction of variance unexplained depending on the comparison. So for example, if you compare the sensor at minus 450 with the sensor at plus 460, you get this 21.9%. Just to give you an intuition, if we have a fraction of variance unexplained that is less than 10%, that indicates a high degree of collinearity. And in fact, there are many of these cases here. You can see they're marked with circles. For example, the sensor in front of the rear axle, 210 millimeters in front of it, is very closely correlated with the readings from a sensor that is at 310 millimeters in front of the axle. Here are some charts to show how this correlation looks like. There are a million cases here plotted, and the sensor at 460 plus and the sensor at 610 plus, they are when they are cross-plotted, you can see this scatter plot and the high correlation that is associated with it. Here's another one, sensor at 210 and sensor at 310, also strongly correlated. There's also some correlation here between these two, sensor at minus 450 and sensor at minus 300. So Obviously, some TSD slope pairs are highly correlated, and the cross plots can be served as a quality control tool because you can plot your own data and assess the quality of it. And if there is something that is plotted completely outside the scatter plot, it means that there is some anomaly and it is worth looking into. Obviously, random noise can be added to the calculated entities that was shown in the study, so it can make it more realistic. I'd like to thank Mehdi and Leo from BUST for discussing this idea and coming up with this approach for quality control. The million cases are published and freely shared. You can just use this QR code or look at this DOI, and you can get a million pavement systems and a million deflection slope sets for each of them. Thank you.